So welcome everyone. Uh, Thanks for coming. I'm super excited to be here. Welcome to Galvanize in beautiful San Francisco. All of what I'll be presenting is here at this URL, github.com/current/screencasts. So if you go to that URL, this is what you'll see. This is the top level for a directory with a bunch of screencasts. And I've put this big link here, Introduction to D3.js. So if you click on this link, you'll get this GitHub repository or directory with all the examples. And then if you click on Slides and Code Examples, this is what I'm showing over here. My name is Curran. I recently got my PhD from University of Massachusetts in Lowell. And during that time, I created a library called model.js, which is a functional reactive programming library that makes it easier to create reusable D3 components and then assemble them into linked views. So here's one that shows population, and you can hover over time, and it slices the time that's used as input to the map. And you can zoom in the map, and that filters the input to the timeline. So in January, I drove across the country, and I started working at Alpine Data Labs in February. So Alpine Data Labs is a big data analytics company for enterprises. And so I'm working on data visualizations there. And I'm working on this open source project called Chiasm, which is based on model.js. And it lets you create visualization plugins and then load them up into this runtime environment that's configuration driven. So as the configuration changes, the visualizations change. So this is just to get a sense of what I'm working on right now. Let's start talking about D3. So D3 stands for data-driven documents, and documents being web documents, HTML documents. It was created by Mike Bostock and Jeff Hare. So Mike Bostock has done some amazing work. He's a very prolific person. He's now working at the New York Times. And Jeff Hare is running a research group at the University of Washington, and they're continuing to evolve their D3-based visualization stuff, which includes Vega. That's their sort of main project. So D3 came out of this older project called ProtoViz. So if you look at ProtoViz, it says like, well, this is no longer maintained, it's been replaced by D3. But this is where some of the origins of the library come from. And a lot of the algorithms and ideas are from ProtoViz. There's a great academic paper on D3, and I would encourage you to read it. It's really good. And with D3, there are tons and tons of examples. So here's a literally infinitely scrollable list of examples put together by Christoph Viau, or Vau, I don't know how to say his name. So, I mean, this is amazing for D3 practitioners because you can find something that's kind of like what you want to make and then look at the code and see how it's done. But if you're just first getting started, all these examples can be a little overwhelming to take in. There are also tons of libraries based on D3 that try to make it easier to use D3. So this is a slide from Christoph Vau's presentation that he gave at another meetup. So here's a list of all of these different libraries that are based on D3. And some highlights are NVD3, which was popular for a while, but it has some licensing controversy. Vega, which is created by Jeff Hare. And DC.js is pretty cool. It lets you link charts together interactively. And that can also be overwhelming. D3 has a vibrant community and a great mailing list, the Google group. So if you have questions about D3 or you want to share some of your work, this is a great place to ask questions and get feedback. So what got me first started with learning D3 was this let's make a bar chart example from Mike Bostock. And this is a tutorial that's a lot of text. So he starts by creating some data and then building up a bar chart with HTML And then there's part 2 where he builds up a bar chart with SVG, which is scalable vector graphics. And then there's part 3 where he introduces scales and axes for the data and margins. And what you have at the end of all this is this bar chart example, which for me is like the prototypical D3 example. So what I'm going to cover has a lot of overlap with this let's make a bar chart example. So here's the code. It's a bunch of code. This is the code that results from let's make a bar chart. And so people call this D3 code, you know, like, and people use this term D3 code, like, oh, let's hire somebody to write some D3 code to make a visualization of our thing. But that's kind of a misnomer because D3 lives in this ecosystem of technologies based around HTML5. So within HTML5, there's SVG, scalable vector graphics, CSS, cascading style sheets, and JavaScript. So these highlighted parts of the code are the parts of this bar chart example that require some background knowledge in these various different technologies. And these are the parts of the code that are really D3 specific, that highlight what D3 gives you. So what D3 really gives you is scales to map data to pixels, and axes to add those labels, and then this really nice construct where you can assign functions to generate values for HTML attributes, like the bars. So in the code examples that I'm going to go through, we're going to create these images with code, and then we're going to create these images with code, with D3. So let's get started. Here's the first example. It's just an HTML template, like just a bare bones HTML page. And I got this from JSBin. So jsbin.com is an amazing little sort of IDE that lives inside the web browser. So you can type some code in here and it appears over here. And you can click Add Library and click on D3 and it inserts the script tag for you. So any of the examples that I'm going to cover, you can copy and paste them into JSBin or other tools like JSFiddle or CodePen, and you can start manipulating the code to try different things out and change numbers or colors or whatever. So this is a bare bones HTML document. The HTML tag is sort of the outer container, and then there's the head, which loads things that you don't see, but they have some effect on the page. And so the head gets completely loaded before the body, and the body contains stuff that you see on the page. So here it says hello HTML, and here on the page, the rendered page, it says hello HTML. This next example introduces SVG. So SVG stands for Scalable Vector Graphics, and the Wikipedia page is pretty good for scalable vector graphics. And the idea with SVG is that you define the sort of the model of the shape, like the definition of the shape, rather than the pixels that represent the shape. So it's called scalable because if you define a graphic with SVG, you can scale it up and it remains crisp like this. Whereas raster images, JPEGs and things, when you scale them, they become pixelated because they're defined in terms of pixels, which SVG is not. So as an example, you can create an SVG tag in the HTML page and then add a rect, which stands for rectangle, and then give it a width and a height. So this is in pixels. This is 100 pixels. A pixel is one of those little squares that makes up the image on your screen. So this is 100 pixels and 100 pixels as a square. So we can change that from 100 to 250, which should also be a square. But this is not a square, it's a rectangle. So it's 250 pixels wide, but it doesn't seem to be 250 pixels high. And does anybody know why this is? It displays like this because we have not set the width and height of the SVG element. And this is a thing that has tripped me up many times when you use D3. If you created an SVG element, you need to set the width and the height of the SVG element itself. Otherwise, you get an SVG that has some default size that's browser specific. So this is how you make rectangles. And then you can also give them X and Y attributes. So this is 50 pixels to the right and 50 pixels down. So note that 0, 0 is in the upper left. As the Y coordinate increases, it goes down the screen. And that's different from like in math where Y goes up. So that's just something to be aware of. So you can make multiple rects in the document, multiple rectangles. So they have different X and Y, the same width, same height, and they have different colors. You can use the fill attribute to define colors. And so fill accepts a CSS color string. You can define colors in a number of different ways with CSS color strings. So this is one way, just picking from a list of predefined colors, and there's a big list out there somewhere of all the colors, the named colors that you can use. You can also use RGB and give it 3 numbers that vary between 0 and 255. So the first one is red, the second value is green, so red, green, blue. This one is blue. And then with this syntax, you can sort of mix and match colors. Mix different values for red, green, and blue to create different colors. And there's also RGBA, and A stands for alpha, which is transparency. So this last value varies between 0 and 1, which I don't know why, it's just a quirk. But that with RGBA, you can make things transparent, or semi-transparent. So that's what this looks like when you use RGBA. And then there are hex color strings. So this is kind of the most common representation of color. It uses this string of 6 characters. The first 2 characters are red, the second 2 characters are green, and the third 2 characters are blue. And so if you look at the built-in D3 color scales, what you get is a set of colors that are defined using this syntax. So here are what some of the colors look like, the hex color codes. This is D3 scale category 10, which you can just sort of pull out and use as a color scale. And there are also a lot of different color pickers out there. Like here's a nice web-based color picker, so you can change around the color and then copy and paste this string in your code to get that color to appear. So that's sort of CSS. There's another property besides fill called stroke, which refers to the outline of a shape. You can draw an outline around a shape with stroke. So the stroke attribute, remember this is an HTML attribute, is the color, but you can also define the width of the stroke with another attribute called stroke-width. So this is in pixels. So here you can draw a stroke of 10 pixels. And you can give fill, or stroke actually, a special value called none, which will make it transparent, which is cool sometimes if you want to have a scatter plot with like just rings rather than filled in circles. This is how you can do it. Here's how you draw circles in SVG. You can have a circle element, and the R attribute stands for radius in pixels of the circle. And if you don't specify X and Y, it has a default X and Y of 0, 0, which remember is in the upper left corner. So just like with rects, you can specify X and Y, but with circles, you need to use CX and CY. I guess that's circle X, circle Y. And this is the center point of the circle. And I think this is because like X and Y are reserved for maybe the corner of the bounding box of the shape. I don't know, it's just some weird quirk. But when you use circles with visualization, typically you want to specify the center of the circle, which you can do with CX and CY. Maybe it stands for center. And just like rect, you can apply stroke and stroke width on circles as well and get the same effect. So here's how you can draw lines in SVG. A line element has these attributes x1 and y1, which are the first point that it draws from, and then it draws to the second point, x2 and y2, and these are also in pixels. And you can use stroke and stroke width on lines, but you can't use fill because there's nothing to fill, it's just a line. So here's how you can draw multiple lines together. Just have a bunch of different line elements on the page and give them different x1, y1, x1, y2. So notice that like the first line, the x2 value is at 100, 150, and that's the value of the x1, y1 of the next line. So the next line starts where the previous line ends. But this is not really ideal because if you make, say, a line chart, you want to think about it as one shape, so not three different ones. So SVG gives you a construct for doing that, which is a path, SVG path. So SVG paths are a little strange. Like they have this D attribute. I don't know why it's D. And you give it this string, which is an expression in this domain-specific language for paths. It's really well documented and it's very powerful. You can make all kinds of shapes with paths and Bezier curves and things. But the basic syntax is this. M is a move to command, and you give it X and Y delimited by a space. So this will move to 50-50, which is the first point. And then L is the line to command, which will make a line between whatever point it was at before and whatever point you give it. So X is 200, Y is 150. It's 200, 150. So this is how you make a line using paths. And you can also make a bunch of connected lines with a path. So it moves to 50-50, and then it makes a line to, again, this is X and Y, and then it makes another line from there to the next set of coordinates, and so on, 3 times to get these 3 lines. You can apply fill to a path as well, and this is what happens. And this is, see, it's not connected. It's not a closed path. This is because this path is not closed. It doesn't specify that it's closed. You can specify a closing path with Z. If you put Z at the end of this string, it will close the path. So this is the difference between D3 line layout and the D3 area layout. It gives you these different kinds of paths. So given the stuff that we've covered so far, we can make something that looks like a scatter plot, roughly. So these are just 2 rectangles, 2 gray rectangles, and then a bunch of circles that have the same radius. So this is kind of like a scatter plot. Notice this circle here. It has coordinates of 0, 0. But in visualizations, like typically we deal with this smaller rectangle that's like the inner visualization rectangle as opposed to the whole SVG rectangle. So let's say that like we want this point to appear here inside the inner visualization rectangle. We can move a whole group of SVG elements with a G tag, SVG group tag. So G right here. So if you make a group, you can put elements, any kind of SVG elements inside that group, and then you can assign a transform to that whole group. So this particular transform will translate everything. And this is X and Y. So it translates everything over, actually in the screen, over this way, 50 pixels. So now we see that this thing, this circle, which is 0, 0, is actually at the corner of the inner visualization rectangle, which is more like what we want. So similarly, this is kind of like a bar chart. You have these 2 rectangles that are gray that represent the axes, and then again we can put the rects inside of a G element and move them all over to be inside the inner rectangle. And these are just rects like we had before. And here's something that kind of looks like a line chart. Here's the SVG structure. It's a path with this weird path string that makes the lines. But you can also put this inside of a group and move it over 50 pixels. So these are roughly the structures that you get when D3 code constructs the SVG. So far we haven't really touched D3 at all. We've just touched HTML and SVG. But this is sort of the basics of SVG that you need to know to understand a basic D3 example. Oh, resizing it, making it bigger and smaller? Oh yeah, you can.
But that's part of D3, that's not part of SVG.
Well, SVG has width and height, right? So if you wanted to have this resize, you need to write some JavaScript that listens for that change event, the resize event, and then get the width and height of the whole page. And then with D3, you can set the values of the width and height attribute on the SVG element based on those values that you get. So D3 is more like a glue that connects data or events like with the DOM. Yeah. Your question?
Are you able to switch out some of the values in the D string?
Are you able to switch out the values in the D string? So we'll get to it. We'll get to that. D3 provides some functionality where you can give it a set of points, and then based on that set of points, it will generate this string for you. So you can change your original points and then call that D3 function, and then it will regenerate this string.
Is there any way to invert you know what I mean, the line? So
is there a way to invert this line?
when you draw the line, you have to draw it with the upside down coordinates in a way.
Yeah, I mean, again, with D3, you can write a function that will invert your data before it generates this line. So yeah, we'll see things like that. Yeah, so I think I'll just keep going for now. You can also make text in SVG. So if you have a text element inside of an SVG document, you can give it X and Y and some text inside, and that just gives you this basic looking text. But SVG itself does not give you any way to like style the text and make it look nice. For that we need CSS, cascading style sheets. So here's how you add CSS to a page. You have these style tags, or you can also link to an external CSS file. But this is CSS right here. This is the CSS language. And it's selecting all of the text tags in the document and then applying this style to them. So it's selecting this tag and then making a font size of 2EM. So there's a whole big discussion you could have about how do you set the size of fonts, and I would encourage you to read this Stack Overflow thread. But like, from what I gather, there's this like mysterious wisdom that you should use EMs. So I just do that. But let's say you had multiple text elements. You should use a CSS class. So this is a CSS concept that's sort of universal, like CSS HTML concept. You can assign the class attribute to any element, and then you can use dot whatever that class name is. So in this case, A. Dot A will select, this is a CSS selector. It will select all the elements that have this class that match. So here we're just setting the font size. But if we have two text elements that have different classes, we can assign them to be different font sizes, like this, and different colors. And also, fill and stroke width can be applied through CSS as well. So this selects A, then it applies, these styles. So yeah, fill, stroke, and stroke width can be applied through CSS or through tags of SVG elements. So here's an example where we're applying stroke and stroke width to one of these letters, and that works. While we're on the topic of text, I couldn't help but put something in here about Google Fonts. Google Fonts is really nice. If you go to Google Fonts, you get this big list of fonts, and you can scroll through and pick whatever font you like, and then click this little button here, and then just copy and paste this snippet into your HTML page, and then copy and paste this snippet into your CSS, and voila, you get this cool font. So that's what I did. I just copy and pasted this snippet, and the snippet here, the font family. So this is how you can use Google Fonts. And you can use these in D3 visualizations too. So let's look at what we had before, a bunch of circles. We can apply classes to circles as well, and then use CSS to define the color of a group of these SVG elements. Now I'm going to get into the JavaScript portion of this. I'm going to introduce basic JavaScript concepts. So you can open up the JavaScript debugging tool, which is really essential if you start writing JavaScript code. It's here, JavaScript console. If we run this code, so this is a basic HTML page with a script tag. And when you put a script tag in an HTML page, it evaluates that text as JavaScript. And there's a built-in function called console.log, which you can invoke with a string. So this is a JavaScript string that you put in quotes, and it will put it here in this console. So this is like the most basic JavaScript program that you could have. So JavaScript supports numbers and variables. So var means variable in JavaScript. So you can give a variable a name and assign it a value, and then you can pass it into console.log to see what it is. So if you're ever going through any code and you don't know what a certain value is, you can type console.log and see what it is. So this is what a number looks like. It's just the number there. A string, which is a sequence of characters, is in quotes. And JavaScript, you can add things together. So JavaScript is loosely typed, so you can add things together that are of different types. So this is what happens if you try to add a number and a string. It sort of assumes that the number is a string, and it adds them together like this. This is called string concatenation. And this is something to be careful about when you work with data, because you need to transform strings into numbers if you want to treat them as numbers. And this is something that trips up a lot of people when they start working with D3. Like, for example, if you have 5 as a string and you try to add it to 5 as a number, you get 5, 5. It concatenates numbers together if one of them is represented as a string. So the solution to this that you need to implement when you parse data is parsing a floating point number, which is like a continuous number, from the string. So JavaScript has this built-in function called parse float. So you can parse this 5 string into a number, and then when you add it, you get 10 out. This is a magical, mysterious voodoo trick that just works, that you just sort of need to be aware of. I don't really know why this works, but just to be aware, you see this a lot in D3 examples. So this parses a string into a number. So JavaScript has arrays. An array is a list of things. And so here's how you make an array with square brackets. And if you console.log the array, it will represent it like that with brackets. And here's how you access different elements of the array. So this is called the array index. Array indices start at 0. So if you want to get at the first element, which is 1, you access my array at index 0. So index 0 prints out 1. So, and also we're adding just this string. Index 0 is plus, which is string concatenation, my array at 0. So this is sort of basic JavaScript working with arrays. And arrays have a special property called length, which is the number of things that are in the array. So if you access my array at myArray.length minus 1, you get the last thing in the array. And this is sort of in general how you can access the last thing in the array. And JavaScript also has objects. So JavaScript objects are different than like Java objects or objects in other languages. JavaScript objects are pretty much key value pairs, where these are the keys, like X is a key, and you can use a key to look up a value. And these are the values, like 5 and 10. So if you console.log an object, you get a nice representation of it. And if it's a big object, Chrome gives you this like really nice navigation thing where you can like drill down into it. You can access object properties with the dot notation. So my object .x will give you 5. And you can also access properties with the square bracket notation, where you give it a string as the name of the key, as the key. So this notation is useful if you don't know what the key will be. Like you can store the key in a variable and then access based on whatever the value of the variable is at that time. So these are the different ways that you can access values within JavaScript objects. So you can combine arrays with objects. So you can have an array of objects. So this is what it looks like, square brackets, and then different objects delimited with commas. So here's a bunch of objects that have X and Y properties. And you can access like the first element using this notation, and then extract the X value from that object using the .x notation. So in this way, we can print out the values of like x0, y0, y1, y2, you know, like that. So this is the structure that you get when you parse CSV files. So we'll come back to that idea. JavaScript also has functions. So this is how you define a basic function in JavaScript. Function square, so this is the name of the function. These, what you put in the parentheses are the arguments to the function. So when you call a function like this, square of 5, x gets the value of 5, and then you can return a value from a function, and then that's what gets sort of output when you call the function, and then we're calling the output of the square function, or I mean, we're passing the output of the square function into console.log. So right now it's printing 25, which is 5 squared. So this is a basic JavaScript function. But note that in JavaScript, functions are like first-class objects. So another way of defining that function is like this. Have a variable called square, and then assign it to be that function. So this is how JavaScript is a functional language. You know, functions are first-class objects. So you can pass functions into other functions, which is a lot of what D3 does. And there's also this construct called for each with arrays. So every array has a function called for each on it. And you pass a function into that. And that function gets invoked for every element in the array. And one of the sort of D3 specific conventions is to use this name D to represent the data element. So this function gets called, and D gets assigned to first this object, and then this object, and then this object, and it goes all the way through. So this logs the X and Y values for all of these objects. So introducing CSV and D3. So this is the first example where I'm including D3 on the page. And I'm including D3 from this big URL from CDN.js, which is a nice content distribution network. So they host different versions of libraries. One of them is D3. So one of the functions that D3 gives you is d3.csv. And the first argument to d3.csv is a name of a file that is right next to that HTML page. So in this example, it's data.csv. This is what a CSV file looks like. It's comma-separated values, where each row will get transformed into an object. So the first row contains the like the column names, and then all the other rows are the values for each row of the data table. So for example, the X value of the first row is 100, and the Y value of the first row is 100. So d3.csv will load that file, and then the second argument to d3.csv is a function that takes as input the array of objects that results from parsing that CSV file. So if we look at the console output from this code, so it's X plus a comma. So it's taking the X value and putting a comma next to it and a space, and then the Y value. So this is what it looks like. It's pretty much regenerating the CSV file. I love the infinite recursion there. That's so cool. Anyway, yeah, that's something to be aware of. Like when you start working with CSV, you need to run an HTTP server locally on your machine in order to load files. Right, right. If you don't specify a full URL, it just looks in the same directory as the page where the page is. So when you load the D3 library onto your page, it introduces a global object that's called D3. So D3 is an object, and it has properties that are functions that you can invoke. So one of the functions is CSV. Yeah, so this is how you load CSV files with D3. So if you load the CSV directly and you try to, let's say we want to add the X value with the Y value for each of these objects. And so like 100 plus 100 should be 200, right? But if we try to add the values, this is what we get, 100, 100. Because d3.csv just reads the values, all of them as strings. So that's why D3 provides an alternative way to call .csv, where the second argument is a function elements as like a pre-processing step. So here it's called type, and that's like just a D3 convention. And so it's parsing the strings. Like d.x, when it comes in from the CSV file, is a string. And when you call parse float on d.x, so d is one of the data elements, you can assign that number, no longer a string, to d.x. So it sort of overwrites the string with the because this, like you could return some other object, but it's just returning the original data object with the replaced strings with numbers. So this time, when this function gets called with the array of objects, these are actually numbers. So when you add x with y for the first row, you get 200, which is the correct behavior. So you need to do this when you parse any numerical data, and it's really important. So you can also use that plus notation when you parse all of the objects. And this, something like this, function type and then with these pluses, you see this a lot in D3 examples. So this is what it means. It's parsing all of the strings into numbers. So a lot of what D3 provides is scales. So scales, in this case a linear scale, it transforms numbers from data space into pixel space. So let's say you have a field in your data that varies between 0 and 1. This is the domain of the scale. So the domain of the scale, so I'll run through this code. d3.scale.linear is a function, and when you call that function, it creates a new instance of the scale. And on that instance of the scale, you can set different properties that persist using this notation where like scale.domain is a function, and when you call that, it will set the value of the domain of the scale. And the D3 convention for this is you give it an array. The first element of the array is the minimum value, and the second element is the maximum value. So here it just goes between 0 and 1. And then the range is in pixel space. And then you can call scale as a function, and the input to the scale function is the value from data space. And then the return value is the value in pixel space. So if you give it 0, it returns 0. If you give it 0.5, which is right in the middle between 0 and 1, it will transform that into pixel space and give you 50, because 50 is right in the middle between 0 and 100. And if you give it 1, it will give you 100. So it like projects from data space into pixel space. So notice that with this code, we're creating the scale, and then in separate JavaScript statements, we're setting the domain and then setting the range. All over the D3 library, you have this pattern of method chaining. So look at this code here. It constructs a linear scale, and there's no semicolon at the end of the line. So it's just one JavaScript statement. So you could write it as one long line like this. So it's creating the scale, and in the same statement, it's setting the domain, and then it's setting the range. And this is because when you call .domain, it actually returns the scale. So this is exactly the same as the previous code, where you're calling scale.domain, scale.range, but you can use method chaining to sort of compress that all into one statement. And you see this in D3 a lot. It's method chaining. And there's also getter-setter functions. So these are setter functions. And this is another thing that's sort of all over in the D3 library. If you call domain without any arguments, it acts as a getter function. So you can get the value of the domain. So if I console.log scale.domain and call that, it will return that array, which is the domain of the scale. So that we specified earlier, right, exactly. So here it's being set, and here it's using the same function on the scale without passing any arguments. And if you don't pass any arguments, it returns you the value that was set before. So this method chaining with getter-setter functions is like all over D3. It's sort of how D3 is designed. So we talked about linear scales, which map data space that is numeric to pixel space. There's also ordinal scales, which deals with data that has like discrete values. So the domain and range of an ordinal scale are ordinal, means like it's ordered things that are unique and distinct. So like the domain of an ordinal scale could be like A, B, C. And then the range could be apple, banana, coconut. Like, you know, A stands for apple. So if you evaluate the scale and give it A, it will return apple. This is what a D3 ordinal scale is sort of. Yeah, you need to have the same number of things. You could have more things in the range than in the domain, but the non-overlapping pieces will just never get evaluated. Yeah. Like, for example, if you use one of those D3 color scales that has like 20 colors, you don't have to use all 20. You could just use like the first 5. So that's just creating a D3 ordinal scale. But ordinal scales have other functions for setting the range. Like here's range points. So if you use range points, you can give it this range in pixel space, 0 to 100, and it will automatically subdivide that into 3 things. So, or in this case, 4. I gave it 4. So 0. So if you give it A, it gives you 0. If you give it B, it gives you something that is like 1/4 of the way, or I guess 1/3. Yeah. So I mean, the first element in the domain corresponds to the minimum value of the range, and then the last thing in the domain corresponds to the maximum value, and it evenly subdivides everything in between. And notice that this gives you like 33.33333, and if you assign that to like an XY of an SVG element, it gives you this sort of blurred line that's not crisp. So there's an alternative thing called range round points that rounds it to the nearest value, which will give you sort of more crisp shapes if you use it with SVG. So here's how you construct DOM elements. So D3, like I think of D3 really as a DOM manipulation library. So the DOM is the document object model. That's what gets sort of created from HTML. So here's what it looks like. There's D3.select, and D3.select is like one of the main, like fundamental D3 ideas. It's kind of like jQuery selections, but it's a little bit different. And this string is a CSS selector. So if you say D3.select body, it will select the body element of the page. And then you can call .append, which will create an SVG element and append it to the body. And then you can call svg.attr, which stands for attribute, which sets an attribute of that element. So you can set the width attribute and the height attribute, for example, like this. And then you can call svg. So these methods are D3 selection methods. And so is rect. So you can create a rect element and append it to SVG, and then set XY width height of the rectangle through JavaScript, through D3. So this is how we can construct exactly this structure. So in this page, there's one version of this that's HTML and one version that's generated dynamically through JavaScript. And when we look at the result, we see them both, and they look exactly the same. And these are two different SVG elements. And the HTML layout just sort of moves one to the right of the other. So this is how you can construct DOM elements with D3. And again, you can use method chaining. So you can say d3.selectBody.append SVG, and then you can chain .attr width, and that returns to you that selection again, so you can chain more and more methods. And then this .attr in the end returns that selection of the SVG element, so that's what gets assigned to the SVG variable right here. So this is sort of the duality of chained versions of things versus non-chained, and this is like sort of also like prototypical D3 pattern that you see a lot in D3. So here's sort of the complete D3 pipeline where you have an array of numbers, which is the data, these are the input. You can set up a scale that maps from the data domain, which is 1 to 5 in this case, to the pixel domain, which is 0 to 200 in this case. So here's the sort of meat of the D3, like what D3 gives you. And this is sort of a tricky thing. svg.selectAllRect .data .enter .append rect. So this is what this is doing is it's creating a it's binding data. So it's called like data binding in D3. D3 data binding is this. svg.selectAllRect will give you a selection that contains all of the existing rect elements on the SVG. And in this case, there are none because we haven't created any yet. And then we call .data and pass it in this array of numbers. And so now this D3 selection has this information that, okay, there's no rects at all, but there's this array of data elements. And then when you call .enter, it gives you what's called a virtual selection. So all this stuff after enter will execute only for the case where there's no DOM element, there's no rect, but there is a data element. So that's like the data elements are entering into the picture. So it's a specific instance of a more general pattern, which will become clear later. So what this is doing is, so the enter virtual selection, in this case, is triggering on all of the data elements because there's no rects to begin with. So in the enter case, it's going to append a rect and then set the y attribute of each of those rects to be the return value from this function when this function gets called with that particular data element. And this will get called for every data element. So this is really what D3 gives you. It's a nice syntax for assigning attributes on SVG elements as functions of data elements. So in this case, it's assigning y to be the result when you call the scale of that data element. So for example, if you call scale of 1, so in this case, like when it evaluates the first data element, d will be 1, and then it will call scale of 1, which will return 0. So that's why the x-coordinate of the first rectangle is 0. This attrx takes as input a function. So look at the previous example, a function of the data element, and we're just taking that data element and calling the scale function. So this is kind of redundant. We could just pass scale directly in as the x attribute like this. And you see this sometimes in D3 examples. This also works.
Is it returning the value for scale evaluated with the current element?
Yeah, exactly. So for each of the data elements, it calls scale as a function and then uses the return value as the value for the x attribute for each of the rects that get added.
The post runs? Or no?
No, because so this is functional programming. So like scale is an object that has methods, but it's also a function that you can call. And so, yeah, D3 is calling that for every data element. So this code here is like sort of a standard pattern that you see with D3, and a lot of people like don't understand it and just like accept it and then copy paste it and then change it, you know, which results in code that doesn't behave correctly. So I'm going to try to explain that right here. So what this is doing, it's only creating, well, that's what the next couple of examples are for. So that big chunk of code can be split up because of the D3's method chaining design. You can create this rects selection as svg.selectAllRect, which there's no rects yet, .data. So this is a D3 selection with data bound to it. So rects.enter, you know, it's doing the same stuff as before, but now it's just split up into two different JavaScript expressions. This pattern was designed so that you can have data that's updating and changing. So this data array will be changing, and as things come and go, D3 will handle those changes elegantly. So let's look at this. We can have a render function, and we can call the render function multiple times with different arrays of data. So this render function takes as input an array of numbers and a color that it will draw these things as. So at first we call it with 3 elements. It creates these red rectangles, you know, sort of as we would expect. And the desired behavior of this is when we call it with these 5 elements and blue, all of those things should be blue. That's the desired behavior. But what we're getting is only the last 2 are blue. This is because we're using enter, and we're only setting the x, y, height, and fill on enter. So that's the enter is when there's more data elements than there are DOM elements. So when we call this function the second time, there are already 3 DOM elements. So svg.selectAllRect will give us those 3 red rectangles. And then, so then when we use .enter, all this code will only execute for those 2 new data elements that have entered into the situation.
So if the second line there said, instead of 1, 2, 3, 4, 5, it said like 4, 5, 6, 7, 8, 9, would enter still execute, or is it caring about like the number?
Oh yeah, it's not caring. In this case, they're the same, right? But it doesn't care about these values. It could be like 0, 0, 0, and still it would not touch the first 3 rectangles. It just cares about the number of elements in the array. Yeah. So enter does not update data. Actually, this gets to exactly what you were talking about. So the first time we call it, we give it 1, 2, and 2.5. See, this is the 2.5. It's not quite spaced exactly the way we want it to be. And then the second time when we call it, we give it 1, 2, 3. And the desired behavior is that this rectangle should move to be in line, to be at 3. But it doesn't. And this is because enter doesn't update data. It doesn't handle when data updates. It only handles when new data elements are added that weren't there before. So D3 has a way to solve this, is that you have different phases. You have an enter phase, and all that the enter phase should do is like create the DOM elements that weren't there and set attributes that will not change that depending on the data. And then everything that depends on the data should be set in this update phase. So we have this selection bound to data, that's rects, and then when we call rects.attr, it assigns that attribute of all of the rects that match up with the data elements. So these functions will be called, like the scale function here, will be called for every single data element. So this is why it's called the update phase. Right, it's a totally different thing. So rects.enter will create the elements, but this update phase will set all the values. So again, we're calling render with 3 elements, red, and then the second time it gets called, because we're using the bound selection, not the enter virtual selection, it will make them all blue, and it will make them all spaced the right way based on the new data. This is update, D3's update thing. But this is also not ideal because like Y, width, and height are constant. They don't depend on the data, So it's setting Y to be 50 every time that we call render, which is unnecessary, So those sort of more static properties can go in the enter phase. That's really what the enter phase is for like constructing the basic framework, the basic DOM structure, and then the update phase is for updating that depending on the new data. There's another phase that I haven't mentioned called exit, and this is like typical D3 phases of visualization. Enter, update. So enter handles new elements being added, but what if we have a situation like this, where we call render 5 elements, and then we call it again with only 2 elements, and we say those elements should be green. The desired behavior is that it should remove these 3 blue elements, but it doesn't, because we've only handled entering elements, updating based on new data, but there's another thing that we need to take care of, which is exiting, when data elements exit the scene. So when there are less data elements, then all of the SVG elements that were there, like as remnants of previous data, should be removed. And so that's what D3 exit is for. So this is how you can use this functionality of D3. Rex.exit, this is another virtual selection that only triggers in the case where there's less data elements than DOM elements. And then .remove will just remove it from the SVG completely. It will throw away that DOM element. So now we're in a position where we can actually set things dynamically. So see how it's changing now, it's updating. So what I'm doing, I'm using set timeout that takes as input a function and a number of milliseconds to wait before executing that function. So 1 second after the page loads, it will call render with these things, and then 2 seconds it will call this, and so on, with different sizes of arrays. And I'm going to refresh the page and you can watch this run. So this is like the typical D3 pattern that should really be applied, in my opinion, every time you write D3 code. Because a lot of those examples that only use enter are like, simple D3 examples that like demonstrate a visualization concept. But when you try to copy and paste that into a situation where the data is dynamic, it doesn't work. Because that example code only handles the enter case, not update and exit like this. So the rest of my examples will be... Now let's visualize some data. We have from a previous example this array of objects, my array of objects, which has x and y values. And if we call render with my array of objects, so this is a variant of the previous render function that uses circles instead of rects. So svg.selectAllCircle, which is there's none yet, first time render gets called, bind it to the data, which is the array of objects with x and y properties, and then on enter it will create a circle that has a radius of 10. So that's static, doesn't depend on the data. And then in the update phase it will assign x and y to be the direct values of x and y. It's not using any scales. This is because it's already in pixel space. We don't need to project it using scales. And exit, in this case, it's never executing, but I think it's a good idea just to have it there in your D3 code in the case that you want to make it dynamic and then and set the data and remove elements. Yeah?
If you were to set a breakpoint if this was executing, would you see the circles flash, at 0, 0 and then reposition themselves to it?
No, because JavaScript is single-threaded, so only after all of this executes does the browser rendering engine actually go into effect. So like all of this stuff gets executed before the SVG rendering engine starts to try to render this stuff. So I'm not 100% sure, but I think in general, if you use JavaScript to change around DOM elements, only after your JavaScript flow control like stops running, the browser will sort of update its rendering based on the new DOM structure. So yeah, you never see the circles flash at 0, 0, even though they are in that temporary state where they don't have a CX or CY. So yeah, this is how you can visualize things as circles. And then here's integrating the CSV parsing. So here's the data.csv, which is the same thing as we had before. And now we're calling render on the result from loading the CSV file and parsing the values into numbers from strings. So this is sort of starting to look like a scatter plot, right? It's almost there. And what did I do here? Oh yeah. So in this example, we're calling d3.csv, and then we're giving it a function that takes an array of objects, and then we're calling render with that array of objects. And so we could it's a little redundant. We could actually pass render as the third argument here as a function. So that's like a functional simplification of the code. So the next example does that. d3.csv type and then render. So type gets called for every single row of the CSV file, and then render gets called with the array of objects after it's loaded. So this is the structure that we'll see in all the following examples. Yeah, there's a render function that gets called once the CSV file is loaded and parsed. So introducing the Iris dataset. There's a great site called the UCI Machine Learning Repository, which has a bunch of example datasets, and one of them is this Iris dataset, which is used a lot in like machine learning to test out machine learning algorithms. And it's about flowers. So it looks like this. Each row is a flower. So there's sepal length, sepal width, petal length, and petal width. So sepal and petal are different like biological terms for like different parts of the flower. And depending on these measurements, you can predict which species it is. So there's like Setosa species and versicolor and like the different species of iris, right? And it turns out that you can use machine learning to predict the species given these measurements. But it also looks nice if you just visualize it. But before we visualize the data, we need one more little piece, which is computing the minimum and maximum value from the data. So if you have an array of numbers, how do you know the minimum and maximum value? And D3 has functions that do that for you, d3.min and d3.max. So d3.min takes as input for the first argument the data, the array of objects, and then the second argument is a function that's used to access one specific property from each of those objects. In this case, sepal length. So it's computing the minimum value of the sepal length across all the entries. So that gets assigned to this variable min. And then the same thing with max. It computes the maximum value. And so then if we console.log min and max, we get these two numbers. If we put it as an array, that's what the scales expect as the domain. An array where the first element is the min, the second element is the max. This is what we get. An array of these two numbers, the min and the max values. There's another function called d3.extent, which actually computes the min and the max in one function call. Rather than like iterating over the list twice, you can iterate over the list once using d3.extent. It computes the minimum and the maximum and returns that array where the minimum and the maximum in an array. So we can sort of combine everything that we've covered so far to make a basic scatter plot. So we create an SVG element with D3. we create linear scales and set the range, which is pixel space, to be between 0 and 250, which is the size that we arbitrarily picked for the SVG. So it's loading the iris.csv file. It's parsing all the numeric fields like this in the type function. And then it's calling render once the file is loaded and parsed. And what render does is it sets the domain of the Y scale to be the minimum and maximum values for sepal length. So this is like one big expression that computes the minimum and maximum with d3.extent and then passes that array into the domain of the X scale. And similarly for the Y scale. It's using a different property though. So here, it's the same D3 pattern where you bind the data, you handle the enter case, where it creates a circle with a fixed radius, and then the update case, and then the exit case. The update case assigns the CX property, which is the X coordinate of the circle, to be, for each object, for each data element, the sepal length passed into the X scale. And it's important that these match. The X scale domain uses sepal length, and the X scale, when it's evaluated, also uses sepal length. These need to match up. So this is how you create a basic scatter plot. But one thing to realize is that the range of the X scale goes from 0 to 250. So the minimum value for the petal length, which is assigned to the Y scale, the minimum value will be at the top. So this is the minimum value up here. But really what we want is the minimum value to be at the bottom. So it sort of corresponds with what people expect when they look at a chart. So the way we can do this is just invert the range. So the minimum of the range, which is not really, it's not less. So the first value of the range is 250 and the second value is 0. So this will invert the plot to be what we would expect. I like to, so this is a little refactoring where rather than hard coding the size, I'm just extracting it into a variable at the top of the file so you could easily change it. And also circle radius, rather than hard coding the circle radius, I've extracted it into a variable and then use circle radius in the code and also use outer width and outer height in the code. And I've used the name outer width and outer height because it's the size of the SVG element. But later on we're going to have an inner side of the visualization area, like inside where the axes are. Yeah.
So what do you want to add all these circles to each?
Yes. Yeah, exactly. So that's coming next. So right now, yeah, we're just appending the circles to the SVG element itself, which works. But if we have axes and labels, we're going to have to move those sort of to the center. But first, rather than hard coding the values that we use for X and Y, like here, the code that computes the domain of the Y scale has sepal_length in it. And arguably, I just prefer to have code where that's generalized, so you don't need to worry about hard coding whatever field it is. So what I've done in the next example is use variables for the names of the X column and the Y column, which sort of makes the code a little bit more clean in my opinion. You can access D at X column. So this now is using the square bracket notation rather than the dot notation for extracting the value from an object. So yeah, this is how you can sort of generalize the code a little bit. So now all the configurable things are isolated at the top of the file, and the data specific things are isolated at the bottom of the file.
Just have the iris CSV and then you open up this file and it'll be clear what it's doing.
Yeah, or if you wanted to change the data file, you wouldn't need to change the visualization code. You would just need to change the code at the bottom and the configuration at the top. Yeah, and so this is sort of moving toward having reusable modules for visualization where you can plug in different data sets. So using D3 scales, we can also have a radius column where the radius of the circle depends on some data values. So similarly, I've introduced a variable for the radius column name, and then an R scale, so R stands for radius, which is also a linear scale that goes from Rmin to Rmax, which I've defined up here to be 5 and 20. And again, computing the domain from the minimum and maximum value for the configured radius column, and then assigning the R property of all the circles based on evaluating the R scale for the value of the data at the R column. So it's almost exactly the same as X and Y, but now we have another sort of dimension that we can express visually in the visualization. So now this is showing 3 columns of the data set rather than 2. And we can do something similar for color. So notice here that we can use CSS to apply color to all the circles. And we can also use CSS to draw transparent rings, which I find is just, it looks really cool. And you don't get this like over plotting where you can't see like how many things are actually there. Setting the fill to be none, so it's like it's not filled in, it's empty, and then just having the stroke, which is the outline, be 2 pixels for each of the dots. But let's say we want to see what species these different iris flowers are with color. So we can also add a color column. So here's how we can represent another column which is not numeric with color. So let's see what the code looks like for this. There's a color column variable as well, species, a color scale, and we're using d3.scale.category10. Something that's built into D3. It's just an ordinal scale where the range is this array of colors that are carefully chosen colors. There are only 3 values that we're using as the domain, but if there were more, it would use these colors. We're not setting the range because that's sort of built into this category 10. And we're also not setting the domain because D3 ordinal scales have this special behavior where like for every unique value that it sees as automagically, it's like a little too magical for my taste, but like we could set the domain manually, but right now it's just assigning the colors based on whatever it sees first. It's the order in which it sees the unique values. This is why the code works. So we're applying, we're using the stroke attribute of the circles and setting it to be, you know, the result of the color scale using the color column. Well, category 10 from D3 is a pre-configured ordinal scale that has the domain configured already. Well, how do you override that? You just, yeah, I could have had an example that did that, but I don't. You can say D3, color scale equals D3.scale.ordinal, and then you can say color scale.domain equals an array of color strings that you can manually pick. Yeah. I mean dot range, not domain. Domain is from the data. The range is the colors. Yeah, so you could do it like that. And you could use like a color picker, to pick the colors, copy and paste the strings, and put it into the range. So here's just the same thing, but just tweaked a little bit. There's no CSS now, and it's just using the fill property instead of the stroke property. And I tweaked the minimum and maximum radius values. So you get a pretty different picture just by making these localization. So here's another data set, population versus gross domestic product for all the countries of the world. So this is from a project I did as part of my PhD that merged data from the United Nations about population and the World Bank about GDP. And it sort of joined these data sets. So this is what we get. This is what the data looks like. Population, GDP, and then a country code. And then I just had to modify this type function that parses the GDP and population rather than the different iris things. Change the CSV file name here. And then up at the top, I changed the X column and the Y column to be population and GDP. And circle radius is now fixed. So it's the same code as before. So what we get though is all the points are sort of clustered in the corner distribution with the data. And this can be remedied by using log scales. So D3, this is what it looks like when you change it to log scales. You can see this really beautiful correlation. And the only lines of code that are changed is this. D3.scale.linear was changed. The code sort of takes care of itself. So it's one use case for log. So it depends on the distribution of your data. And this kind of distribution comes up a lot when you're dealing with like cities or countries or just a lot of different things. It's a power law distribution. So what if we try to use size in this case as well? So this is what it looks like if we use the same code as before with a linear scale for size. X and size are both mapped to population. So they're all pretty much the minimum size except for these few over here that are almost the maximum size. So how could we do this differently? So like linear scale for size is really not the best for this case. This is what it looks like if we use a log scale for size. Yeah, d3.scale.log for the R scale. But, I mean, when you visualize things using size, it's interesting to ask the question, like, so this is population, right, as size. What if you ask the question, how many people are there per pixel? Per pixel of filled in black area of the circles. And that doesn't make sense if you use a log scale. Because if you think about the area of a circle, it has to do with the square of the radius. If you type in area of a circle into Google, you get this really, really beautiful page that has like the radius and a circle. Oh, and you get the equation. This is what I was looking for. So the area of a circle is pi r squared, where r is the radius of the circle. And what we're doing is changing the radius of all of these different circles. And what we're perceiving with our eye, though, is the area of the circle. So it would be really cool if we could have a scale where we could ask the question, how many people per pixel? And that answer would be consistent across all the circles. So D3 has a square root scale that you can use, d3.scale.square root, which is super cool, right? Here the radius minimum, though, is 1. So if the value of the population is 0, the radius is still going to be 1. So it's not quite right yet. But if we change the code just a little bit to make the minimum radius be 0, and also rather than using the extent of the population for the radius domain, so now we can ask the question, how many people per pixel? And it's 1.08 million people per pixel. And I did the math down here, actually. Yeah, just sort of coming up with a little formula to compute the people per pixel and solving it. So the pi r squared is the number of pixels based on the max radius, and then this is the maximum number of people. So this is an interesting little piece of code that you should be able to grok. rscale.domain, it's getting the domain, which is an array, and it's getting the second value, the index at index 1. The second value of the domain array is the max value for the domain. So this is the highest value for the population. So the highest value for the population divided by the highest value for the number of pixels occupied by a circle gives you the number of people per pixel, which in this case is 1.8 million. So this visualization I find is much more like interesting to look at because it's like the population is true to the size, or the size is true to the population. So it's something to keep in mind when you use size. So let's say we want to sort of resize it by 30 pixels from the top and the bottom. We use an inner width, outer width minus 30, and then we use the inner width in the scales. That's to address the problem with the previous example that these circles get cut off in the corner. You can't see the whole circle. So the population, it's not being really represented adequately. So here's how we can move it over to the left, but how do we move it down from the top? If we just change the size vertically, it'll get squashed from the bottom, but we want to really move it down. So we can use that G element from before. put all the circles inside of an SVG group. So here's what that looks like with D3. SVG.append G. We're appending a group element and then translating it by 30 in the X direction and 30 in the Y direction. But notice how it's still cut off on the right, because we're only subtracting 30 from the outer width. But what we need to do is subtract the 30 that was translated, and then also we want to subtract 30 from the right side, which is really the margin on the right. So the correct computation for that would be the inner width is the outer width minus 30 minus 30. So this first 30 is the margin on the left, and the second 30 is the margin on the right. So rather than having hard-coded numbers, let's make variables to define the margin. So this is how you can use variables to define the margin of the visualization. So these are taken into account when you compute the inner width, and also the scales, and also the translation of the transform of the G element that contains all the circles. Oh, and by the way, the circle code uses G rather than SVG. So it's G.select all circle. That means it will append the circles to the G element, not the outer SVG element. This is using variables, which you could do, but there's a D3 convention to use objects, or to use an object to represent the margin. So this is the same code as before, but just using an object. So the margin has left, top, right, and bottom properties that get taken into account with the scales and translating the group element. So this is how you implement margins. And there's a great D3 margin convention example. So this is what it looks like. You translate by the margin.left, margin.top, and this is the right margin, this is the bottom margin. This is the inner visualization rectangle inside that G element. And the scales use the inner width and the inner height of this. So this is a pattern you see across many, many different D3 visualizations. So I'd like to, this is just a little trick where I use that algebra to so you can set the number of people per pixel. So now I'm setting the number of people per pixel to be exactly 1 million. And so it's just sort of a transformation of that other math. It's not that interesting, but it's useful if you change the data set and you want to be able to compare different data sets. So it's loading another data set. So this is an extract of the GeoNames database, which has a listing of all the cities in the world larger than 15,000 people. But this is filtered to include cities that only have more than 100,000 people. So this is like about 4,000 cities visualized right here. So all the code is the same. It's just a scatter plot. But instead of X and Y being data, it's latitude and longitude. So it kind of looks like a map. Here's the US, here's South America, here's Africa. And you can see India is very dense, and China is also very dense. So here's what the data looks like. It's just a bunch of cities with latitude, longitude, and population. And here's parsing that data. Just minor differences from the previous examples. So in the next example, I just tweaked it a little bit. This is what it looks like if you set the scale such that it visualizes 100,000 people per pixel. But now you have a bunch of overlapping stuff. So we can add some CSS. What I did here is I just added some CSS to make the background black and to make the fill of each circle have transparency. So each circle has a transparency value of 0.2. So now you can see where there are overlapping cities, you can see the density represented as brightness. So now this is more of like a clear picture of the population density throughout the Earth. You can see in India, South India, it's really dense. North India is really dense. And over here in China, it's super dense. But in Africa, there's huge, vast, empty spaces. And also in the US, it's there are a lot of vast, empty spaces punctuated by massive cities like Los Angeles. I think that's San Francisco. And then probably that's New York City. So, I mean, when I made this, I was so happy, so excited. That's so cool to be able to see that, to see the density of people on Earth through this technology. So that's just another scatter plot example, you know. Another data set is temperature in San Francisco for the past week. So this is also a scatter plot, pretty much all the same, except for changing it to be specific to this data set. And this is from this Data Canvas Sense Your City project, and they have an API that you can query to get the data live, like up to the minute, which is super cool. But I've extracted it into a CSV file for this. So here's one example that I made where it's the live temperature data from like 8 different cities, and it's going to load 1 day's worth of time at a time, and it's going to keep loading and keep populating this data. But while that happens, I can select over here, and there are these linked graphs. So it's like just a zoomed in version of the other one. And then when I select over here, it can plot that temperature versus humidity. So this is just one of my little side projects. Here's the temperature of San Francisco for 1 week, visualized where time is going from left to right and temperature is going up and down. But this really should be a line chart, not a scatter plot, right? So in the next example, this is how we use d3.svg.line. And it doesn't look quite right. We're going to fix that. But here's how it works. We append a path element to the SVG group. And then we use d3.svg.line for x and y. So this is a little bit different pattern from, there's no enter, update, exit pattern here because there's only one path element. And so when we call render, we update the scales, just like before, and we set that D element on the path to be line evaluated with data. So this is d3.svg.line. That's a lot of functionality in there. So when you call line with your data array, it will generate that weird string that has like M and L and the different, coordinates, and it will assign that to the D value of the path. So this is one path element, and all the data is expressed in that string that gets generated by this line function, which is d3.svg.line. Really cool. But if you just create the line on the page, this is what you get because it's automatically filled in with black. There's no CSS on this page, but if we add a little bit of CSS that just says, don't fill it in, but give it a stroke, we get a proper line chart. And so now we can use these same tools to make a bar chart, a basic bar chart. So this uses ordinal.range bands, which is similar to ordinal.range points, but rather than subdividing the range into an even number of points, it does that, but it computes a size, like a band. So this is the documentation page for range band. It's perfect for a bar chart. It was like designed for making bar charts. But it subdivides the range that you give it, the minimum and maximum in pixels, it subdivides that into these bars. And you can specify a padding between bars and also an outer padding. And depending on the padding and the number of elements, it will compute the width of the bar. So you can add more bars and it will automatically shrink the bars. You don't have to hard code the width of the bars. That's what d3.ordinal.scale.rangebands is for. Here it is in use. The x scale is d3.scale.ordinal.rangeband. So it's setting the range of the scale. So we're giving it 0, inner width, which is the minimum and maximum in pixel space where the bars should go. But because it's range bands, it subdivides that into 3 sort of chunks, depending on the domain. So that's another thing that's slightly different for ordinal scales. When you compute the domain of it, and by the way, this is the structure of the data. It's a CSV file with 3 entries, 1 entry per city. And so this is showing the population of the 3 biggest cities. Data.map. So this is something that's built into JavaScript arrays. If you call some array.map, you can give it a function, and that function gets evaluated for every element in the array, and then whatever gets returned is put into a new array. So the result from data.map is an array of all of the, in this case, the country names. So it's going to be an array of 3 strings, each of which is a name for a country. And that's getting assigned to the domain of the X scale, which is a D3 ordinal scale. So because we set the domain to have 3 elements, the X scale knows when we evaluate xscale.rangeband, it uses the information from the domain and the range to figure out how wide each bar should be. And then we're setting x, y, and height of the bars. So we assign the x value to be the result of the x scale with the x column data point value, which gives us the leftmost point of the bar. And then for y, we're setting the y coordinate of the rectangle, which remember goes from the top to bottom, 0 is at the top, to be the scale of the y column. And notice that the scale range is inverted, just like it was before. And then we're assigning the height of the bar to be the inner height of that G element minus the result from the Y scale. So it's just, I mean, some tweaking you need to do to get the bars to show up correctly. You know, but so you need to take the height into account to get the bars to show up correctly. So D3.rangeBands takes another argument. We're just giving it the first argument, but it takes as another argument the padding between the bars. So here's just an example that demonstrates that padding. So I have a variable called bar padding, which is 0.2, which is like 20% of the size of the bar. And then it's being passed in there as the second argument to range bands. So now let's add axes. There's a lot of functionality implemented in the D3.axis modules. But this is how we use the D3 axis. First, we need to append group elements to the group element that we already have. One group for each axis. So here we have an x-axis and a y-axis. So the x-axis, we need to translate it by the inner height. Otherwise it would appear at the top of the bar chart, but we want it to appear at the bottom of the bar chart. So that's why we need this translate by 0 in x and inner height in y. For the x-axis G, I'm using this naming convention of putting G at the end because it's the group element that's for the x-axis. SVG.axis, this portion creates an instance of a D3 axis, and then using method chaining, we're setting the scale of that axis to be our x scale, and then we're setting orient, which determines where the text is placed. And for the y-axis, orient is left, meaning the text will go to the left of the actual axis. So in our render function, we use this pattern. X-axis G is a group element. That's a child of our outer group. It's a D3 selection though too. So if you call the function that's called call on any D3 selection, it will apply this function to that selection. X-axis G.call x-axis will sort of apply the x-axis functionality into that group. So if we inspect these elements, we can see that this call right here, this code right here, constructs this whole DOM structure for us. So here's our outer SVG group. Here's the x-axis G group. And then inside of here, it has added another group for each tick mark. And for each tick mark, it has a line, which we're not seeing because the path is like too big. The larger line is occluding it. But then it has text. So this DOM structure is created by D3 axis. And then there's a path, which is sort of the line that goes to the extent of the axis. So this is the DOM structure that you need to be a little bit familiar with when you start using CSS to customize the appearance of the axis. So that's what this next example does. The next example just adds some CSS. So here I'm using the same Google font as before with the same technique. When you create these group elements as children of the outer group, I've changed the code to give them a class attribute so that we can sort of access them through CSS. So when you give a class attribute that has two things separated by a space, that actually applies both of those classes to that element. It's just setting the text and it's customizing the appearance of the lines. So now we get this nicely annotated bar chart. And if we swap around the X and the Y and the width and height throughout the code, we can get a horizontal bar chart, which is kind of a more effective visualization in some cases where you have more bars that you want to show, because you can show all the labels for more bars. Because if you have vertical bars, and if you have horizontal text as the labels, like you just can't put that many. You can only put like 5 on a visualization. This is also customized to remove the vertical line for the y-axis, because it's not really necessary, because your eye can sort of see the association between the bars and the text. This is how you can add a text label to an axis. Like, so this is representing population of these various cities. And it's actually a lot of code to do this, like more than you might expect, but it's just dealing with the quirks of SVG text. So here it is right here. We're adding an x-axis label, so x-axis label variable. It's appending a text element to the x-axis group. Text anchor middle means that it will be centered with respect to the point that you give it. A transform. Actually, I could have done this with just x and y. Whoops. But I'm using a transform. So the x is the inner width over 2, which is like the center in the horizontal direction. And then the y is the x-axis label offset. So I just moved it to be like in a place that looked nice. That's where 55 comes from. And then I gave it a class of label, so that then in the CSS, you can access that class and, in this case, change the font size so that the label is bigger than the tick mark labels. So this is how you can add labels to axes. So we can apply the same axis technique to the other visualizations. So the remaining examples, I'm not going to even look at the code, but I'll just tell you that it's applying the exact same pattern for axes to the different plots that we had. So here's a scatter plot with nice axes, and here's a line chart with nice axes. Thanks for listening.